Dr. Vimla Thetan Rathina Sabapati, Professor and Head of the Department of Electronics and Communication Engineering in Aditya Institute of Technology, Coimbatore. Doctorate in the field of crypt analysis in Government College of Technology, Coimbatore. Postdoctoral Fellow in the Department of Information Engineering, University of Padova, Italy. He is very much interested in research area of cryptography, crypt analysis, electromagnetic interference, compatibility, antenna design, wireless sensor network and communication. He has published papers in international journals and international national conferences. He is a reviewer of journals like DRDO, WSCAS, International Journal of Network Security, and also have a membership in professional bodies like CRSI, IACR, and Computer Society of India.
Welcome to UGC lecture series Communication Electronics for Applied Electronics. In the today's session, we are going to discuss about the noise in PCM. The noise consideration in PCM. The performance of the PCM system is influenced by two major sources of noises. One is the channel noise and another one is the quantization noise. These two noises determines the performance of the any PCM system. If we take a channel noise, so this noise gets added in the channel and this may corrupt the signal, and whereas the quantization noise, this noise will be introduced in the transmitter itself. That is, quantization noise is nothing but the quantization error, that is the error seen at the transmitter side. This quantization error can be controlled, but whereas it is very difficult to control the channel noise because the user do not have any control over the channel, but whereas this quantization noise can be controlled by the user, that is at the transmitter side. If you take the channel noise which is introduced anywhere between the transmitter and the receiver, the channel noise is always present once the equipment is switched on. That is, when the transmitter is on and when the signal is transmitted through the channel noise will always present. It may interfere in any form. The main effect of the channel noise is to introduce bit error in the received signal. That is, the channel noise will produce a bit error. Fidelity of the information transmission by PCM in the presence of channel noise may be measured in terms of the average probability of symbol error. So, this parameter determines the channel noise, average probability of error, and it is defined as the probability that the reconstructed symbol at the receiver output differs from the transmitted binary symbol on an average. For example, if you transmit 1, then at the reception side we have to receive 1. If you transmit 0, then we have to receive 0 at the receiver. And if you transmit 1 and if you receive 0 at the reception side, then there is some error. So, this average probability of error is based on the number of bits transmitted at the transmitter and the number of bits received correctly at the receiver. For example, if 10 bits are transmitted and if all the 10 bits are received correctly, then there is no error. For example, if 1 bit is received with error, then the probability of error is 1 by 10. So, first we have to transmit a known data and then we have to identify the received data and we have to compare with the original data. So, from this we can easily calculate the average probability of error. Then using this average probability of error, then we can transmit an unknown data, and based on this information we can predict the error occurred at the reception side. The average probability of symbol error, also referred to as bit error rate, shortly called as BER, assumes that all the bits in the original binary waves are equal importance. To optimize the system performance in the presence of channel noise, we need to optimize the average probability of symbol error. That is, we have to optimize or we have to control the average probability of error. And the next one is quantization noise. This quantization noise is introduced in the transmitter itself and it is carried all the way along the channel to the receiver. Unlike the channel noise, the quantization noise is signal independent in the sense that it disappears when the message signal is switched off. That is, when there is no message signal, then there will not be any quantization noise. That is, when the message signal is switched off, this quantization noise will be disappear. The use of quantization introduces an error which is defined as the difference between the input signal EM and the output signal V. So, this difference is called as quantization noise or the quantization error. So, this figure shows about the quantization and the original signal, and this figure shows about the quantization noise. Here this is the original signal and this is the sampled signals at, and instead of TS it is sampled, that is at TS, 2 TS and 3 TS we have samples, and these samples are encoded or is converted into quantized signals and then it is converted into binary outputs. So, this figure shows about the different signals, that is this graph shows about the different signals. This continuous line shows about the analog signal, this one shows the analog signal, and then dashed line shows the PAM signal. You can see here a PAM signal, a pulse sampled modulated signal, and then this step signal shows the quantized signal, that is analog signal, a flat top PAM signal and quantized PAM signal. So, all are represented in a single graph, and this one shows about the sampling times. When a signal is quantized, we introduce an error. The coded signal is an approximation of the actual amplitude. The difference between actual and coded value is the quantization error, and if we go for more zones, that is more number of levels, then it results in the smaller delta size, thereby which results in the reduced errors. But if we go for more number of levels or more zones, quantization zones, then more number of bits is required, but here the transmission rate, that is we require higher bit rate for transmission because we use more levels. So, more number of bits is required, higher bit rate is required for transmission, and due to the quantization inherent errors are introduced in the signal. So, this is called as quantization error and this is represented by this del, that is xq of NTS minus x of NTS. If the input is that sampled signal which is of the range minus x max to plus x max, and the total amplitude range, that is the dynamic range, that will be the difference of the maximum level and the minimum level. The maximum level is x maximum and the minimum level is minus x maximum. So, this difference gives the dynamic range, or we can call it as an amplitude range. If this amplitude range is divided into q levels of the quantization, then the step size del is given by the dynamic range by the number of levels. So, q is the number of levels and this is the difference of the maximum value and minimum value. This ratio gives the step size del. So, here in this case 2 x max by q. If the signal x of t is normalized to a minimum value and maximum value of 1 and minus 1, that is we take that positive peak as plus 1 and the negative peak as minus 1. So, in this case what about the step size? If for a normalized signal del takes 2 by q, that is x max minus of minus x max, that is 1 minus of -1, it becomes 2. So, it becomes 2 by q. So, the step size will be 2 by q, and q represents the number of levels. That is, this is for linear quantization. That is, we are going to compute the noise power and signal power, and then we are going to find out the signal to noise ratio for this uniform quantization, that is SNR. And to be specific, it is called as SQNR, signal to quantization noise ratio. Since we are computing the quantization noise, we call it as signal to quantization noise ratio and shortly called as SQNR. If the step size del is sufficiently small, then it is reasonable to assume that the quantization error epsilon will be uniformly distributed random variable. That is, we consider that this error is uniformly distributed. The maximum quantization error is given by epsilon max, which is equal to modulus of del by 2. That is, the range of this error lies between minus del by 2 to del by 2. That is, minus del by 2 is less than epsilon max, which is less than del by 2. If we consider a uniformly distributed a random variable, let us consider here this is a variable x is a variable, and the p of x is the probability of x, and here this is uniformly distributed. That is, if you see here in the range a and b, the value is uniform, that is, it takes a constant value. So, what is the probability density function of a uniform distributed variable? That is, p of x is the probability of x of a general random variable, and here if it is uniformly distributed, then it is given by 1 by the maximum value. So, here what is the maximum value? B minus the minimum value a, that is the difference of upper value and the lower value. This gives the probability density function of a uniformly distributed random variable. If we consider the error is uniformly distributed in the range minus del by 2 to plus del by 2, that is, if we consider that error is uniformly distributed in the range minus del by 2 to del by 2. So, what happened to the probability density function PDF? That is, the higher value is del by 2 and the lower value will be minus del by 2. If a and b are the lower values and higher values, then the probability is given by 1 by b minus a, and if the lower value is minus del by 2 and the higher value is plus del by 2, then what is the probability density function? So, a random variable is said to be uniformly distributed over an interval a comma b, then the probability density function of x is given by f of x equal to 0 for x less than a, and f x of x will be equal to 1 by b minus a for the x that lies between a and b, and again it will be 0 for x greater than b. In our case, this probability density function is given by 1 by 2 del, that is minus del by 2 in the range. So, the higher value is del by 2. So, this is the probability density function, that is 1 by b minus a, that is 1 by del by 2 minus of minus del by 2. So, 1 by del by 2 plus del by 2. So, del by 2 plus del by 2 becomes del. So, 1 by del. So, 1 by del is the probability density function for the quantization error epsilon, which lies in the range minus del by 2 to plus del by 2. So, outside this region, the probability density function is 0, that is for epsilon greater than del by 2 and for epsilon less than minus del by 2, it takes 0 value. Now, we are going to see about the signal to noise ratio. The signal to noise ratio, it is nothing but the ratio of the signal power to the noise power. And here in this case we are going to compute the noise power, that is quantization error power, for a uniform quantization. Here S by N is the ratio which is shortly called as SNR, which is defined as the signal power to the noise power. If the type of the signal at the input, that is x of t will be the input if it is known, and then if we know that noise power, then we can calculate the signal power and noise power. From then we can find out the ratio to calculate the SNR. This SNR is in general, since here we are going to compute the error for quantization noise. So, we specifically call it as SQNR. The noise power is normally given by the ratio of V square by R. Usually the power will be the product of V and I, the voltage and current. But if you take the current can be given as V by R. So, it is V square by R. So, this is one form of representing the power, either V into I, product of V into I, or V square by R, or one more form I square R. So, if you replace this V as I by R, so I by R into I, this gives I square R. So, these are the three forms of representing a power. Here the ratio of the noise voltage, that is square of the noise voltage to the resistance, this gives the noise power, where V square noise. So, this is the mean square value of the noise voltage. Since the noise is defined by a random variable and we assume that the noise is a random variable and it is distributed uniformly, that is epsilon is the noise or error, and the probability density function is given as f epsilon of epsilon. Now, we are going to compute the mean square value, expectation of epsilon square. So, this gives the noise power here, that is if you take expectation of Vx, so it is given as E of x equal to x f of x dx. This fx is nothing but the probability density function. Here we have expectation of x. So, this expectation of x is called as an average of x. So, this is given by x into f of x into dx. Since here we have x square, so we are substituting x square. This expectation of x square is called as mean square value, mean of the square value. So, you see here E of x is the mean of x, and here this is the mean of the squared x. This mean square value, this gives the power, that is since power of x, and here the power of epsilon. So, since this is epsilon is a noise, this expectation of epsilon square gives the noise power. So, expectation of epsilon square is given as integral epsilon square f epsilon of epsilon d epsilon. So, this is uniformly distributed in the range minus del by 2 to plus del by 2. So, the probability density function is given as 1 by del. Just now we have derived how we obtain this 1 by del. So, the range, so from the minus del by 2 to plus del by 2. So, from the lower limit is minus del by 2 and plus higher limit is plus del by 2, and if you substitute this values and if you integrate this equation with respect to epsilon. So, epsilon square becomes epsilon cube by 3 and the limits are minus del by 2 to plus del by 2, and after applying the limit, so 1 by 3 del cube by 8 plus del cube by 8. So, this gives del square by 12 after simplification. So, this del square by 12 is the noise power. The mean square value of the noise voltage is V square noise, and the mean square value is given as del square by 12, and if the load resistance is considered as 1 ohms, that is the noise power is V square noise by 1, that is V square by R. We consider R as 1 ohms for normalized case, then the noise power is del square by 12. This is for the normalized case. Now we are going to find out the signal to noise ratio. This normalized signal power, this may be of any signal, x of t of may be of any type, and the noise power what you calculate is del square by 12. And if the number of bits is V and the quantization level is Q, then the relationship between the number of levels and the number of bits is given as 2. And what is del? The step size. So, which is given as the dynamic range to the Q, that is quantization levels. This it gives 2 times x max by 2 power V. So, this is nothing but Q. Substitute the value of del in this equation and then you simplify. And if you consider the normalized signal power as P, P is the power of the message signal. This signal may be of any type, a voice signal or a sinusoidal signal. We will see for the 2 different cases now. So, if you simplify this 2 x max by 2 power V the whole square. So, this becomes 4 x square by 2 power 2 V divided by 12. And after simplification, if you simplify this, so if you cancel this one, it becomes 3, and if you bring this denominator to the numerator, so the simplified equation will be 3 p by x square max into 2 power 2 v, and v, what is v? V is the number of bits. So, the signal to noise ratio depends on the parameters p, that is signal power, and v, the number of bits, and x square max. So, this is nothing but the maximum level of the signal. So, the maximum signal to quantization noise ratio is given by this equation. This equation shows that signal to noise power ratio of a quantizer increases exponentially with increasing bits per sample, that is it is of the order 2 power 2 v. So, that SNR increases exponentially. Let us assume that input is normalized, that is x max is 1. If x max is 1, then what happened to this equation? 3p into 2 power 2 v, 3p into 2 power p. And if the signal power is also normalized and if we consider it as 1, then the signal to noise ratio is given by 3 into 2 power 2 v. Usually the signal to noise ratio will be expressed in decibels. So, how to express the signal to noise ratio in decibel? Simply if you take 10 log this value, then it can be expressed in decibels. So, if you take this SNR S by N, so here we are taking the 10 log of this S by N gives the signal to noise ratio in decibel. So, 3 into 2 power 2 v, 10 log of this value gives the SNR in decibel. If we compute, that is 10 log 3 into 2 power 2 v, then we will get the equation as 4.8 plus 6 v. So, v is nothing but the number of bits. So, SNR or SQNR is given as 4.8 plus 6 v. V is the number of bits. This is the SNR for signal of any type. If we consider the signal to noise ratio for x of t as sine signal, a sine wave, here the noise power will be of x max square by 2, that is the maximum value by 2. If you substitute this signal power for a sinusoidal wave in this expression, that is general expression. Here we will have P 3 into 2 power 2 into P, and if we substitute this value, and for normalized case we will get 3 into 2 power 2B by 2. So, this will be the SNR for a sinusoidal signal, and if you take the logarithmic value for this, then the signal to noise ratio will be 1.8 plus 6B. So, this is expressed in decibels. V is the number of bits. Let us consider different cases. If V equal to 1, that is only 1 bit, then what about the signal to noise ratio for the first case? This is of any signal. This is for the input signal is sine signal. 6 plus 4.8, so it is 10.8 dB. The signal to noise ratio is 10.8 dB, and here if V is 1, then the signal to noise ratio is 7.8 dB. If V is 2, then 6 into 2, 12 plus 4.8, that is 16.8, and here 12 plus 1.8, 13.8. And as if you increase the number of bits, the signal to noise ratio will increase further. That is, if you consider, if you want to represent a data, a binary data, and if you want to increase the number of levels, then the signal to noise ratio will also increase. For example, if we consider the first case and second case, if V is 1, here 10.8 and 7.8. For each bit rise, if increase 1 bit, then the signal to noise ratio will be increased by 6 dB. If you see here, if we consider this case and this case, for 1 bit it is 10.8 and for 2 bit 16.8. If we go for 3 bits, then yes, another 6 dB will be added. So, 22.8 will be the signal to noise ratio. For 1 bit rise, 6 dB will be increased in both the cases, that is for any type of signal as well as sinusoidal signal. So, we have discussed about the signal to noise ratio for different bit levels. And conclusion, in the today's session we have discussed about the noise in PCM system. Mainly there are two types of noises, one is channel noise and another one is quantization noise. The channel noise gets included in the channel, and whereas the quantization noise is originated at the transmitter. We can control the quantization noise, but whereas the channel noise we cannot able to control the channel noise. And then we have discussed about the signal to quantization noise ratio for a general signal and for a sinusoidal input signal. And then we have discussed about the signal to noise ratio for different bit levels. Questions: what is meant by channel noise? Define signal to quantization noise ratio. What is the signal to quantization noise ratio for 4 bit PCM? Thank you.